In part D of this problem, we're asked to calculate what the pH of this ammonia solution, 0.2 molar ammonia solution, is after we've added 16 milliliters of the strong acid, hydrochloric acid. So the first thing we want to do is to do a little bit of a stoichiometry calculation. It's how we always begin these things. So working in moles, we're going to calculate the proportions of ammonia and ammonium ion. So ammonia is our weak base and the ammonium ion is our conjugate acid, and that's going to kind of direct us as to what type of calculation that we need to do. So in 40 mils of 0.2 molar ammonia, there is 0.008 moles of NH3, and we have no moles of that. So now we need to calculate how many moles of H plus that we're adding. So it was 16 milliliters and the concentration was 0.5 moles per 1 liter or 1000 milliliters. And you guessed it, that works out to be 0.008 moles. So what that means is that in this particular part of the problem, we have reached what is known as the equivalence point, where the number of moles of acid that has been added is equal to the number of moles of base that we started with. So there's no limiting reactant or excess reactant in this case, and what will happen is all of our base will get consumed by our acid. So after this addition, we will have none of our weak base and none of our strong acid. What will happen to our conjugate acid concentration is it will increase by 0.008, leaving us with 0.008 moles at the end of the addition. So what do we have? We have a solution of a weak acid. And how we solve for the pH of a weak acid is by doing a Ka ice table. Now it's important to realize that this is the number of moles that we've calculated here. So what we have to do is turn that into a concentration. So the concentration of the ammonium ion in this case, it's going to be our moles, 0.008 moles, divided by our volume in liters. And we had 40 milliliters that we started with, and then we added another 16 milliliters. As I said, that needs to be in liters, so we've got to times it by 10 to the minus 3. So when I do that, it's going to be 0.008 divided by 0.056. So that works out to be 0.1429 molar. So the concentration of our ammonium ion is 0.1429 molar. So now we can go ahead and do our Ka ice table. So let's set that up. So we've got ammonium ion in equilibrium with its conjugate base ammonia and H plus. The initial concentration of our acid is 0.1429. This is originally 0, this is originally 0. Now it comes into equilibrium. That will go down by x, this will go up by x, and this will go up by x. So at equilibrium, we have 0.1429 minus x of that guy, x of that guy, and x of this one. So this is a Ka ice table, but we can't find Kas in the back of the book for ions. What we have to do is Kw on Kb. So Ka for this is going to be 1 by 10 to the minus 14 over the Ka for ammonia, which is 1.8 by 10 to the minus 5. So when I do that math, it ends up being 5.56 by 10 to the minus 10 is my Ka. Okay, so now I'm in business. So Ka is going to be my product ion concentration over my reactant ion concentration, and that's equal to 5.56 times 10 to the minus 10. So I use the solver to solve for this. So using the solver, x equals, let me just quickly pull that up for us. It is 8.916 times 10 to the minus 6 moles per liter. Now in this case, x is just equal to my H plus concentration, so my pH is negative log of x, So negative log of x, and that ends up being 5.05. So it's acidic, which is good because I know at the equivalence point of a weak base titration, it should be a little bit acidic. So I'm feeling happy about that. I can continue on my path here. At the equivalence point, I've got 5.05 as my pH.